Some time ago I bought this little USB tester for less than £6. It goes under the name UT658 and is made by UNI-T. By inserting it directly into the path, it makes testing of USB powered devices very convenient, but there are shortcomings which I'm going to explain in this video. It's not always showing what's really going on. The current measurement could be better. The capacity metering can underreport what's really flowing in or out of a battery. The documentation is all in Chinese, but digging around on the internet I found this datasheet on the UT658 which lists some of its specs. The input voltage is 3 to 9 volts and the current range up to 3 amps, which means that it may be able to not only show the standard 5-volt USB but also the newer 9-volt charging profiles. Although it says here that it displays overload if higher than 9 volts, in fact it works until 9.99 volts and only then shows the OL. It claims to measure voltage with an accuracy of ±1%. On the current reading it's a bit more complicated. First of all, it will deliberately show 0 for anything below 50 milliamps, which isn't too helpful for a tester used for troubleshooting. I would much prefer it would somehow show if current is flowing, even if it can't display the exact amount. Anything lower than 500 milliamps has an accuracy of ±3%, while currents above 500 milliamps have an accuracy of ±1%, ±2 digits. To help explain what this means in practice, I made this little table which shows the 3 different current accuracy specifications from the datasheet and how they affect the readings. The most left column shows the input current rising from 0 to 3 amps. The next column shows the stated error in percent, 0, 3 and 1 for the different ranges. Calculated out of this, the next column shows the error current. For example, at 1 amp and 1% error, we have a possible error current of ±10 milliamps. The next column is the number of error digits in the resolution of the display. With that, we can calculate the worst case of low and high readings if all tolerances add up. For example, for a real current that is exactly 1 amp, we can expect to see a readout between 0.97 and 1.03 on the UT658 displays that meets its specification. Graphically, this is shown here. The accurate current is shown in green, and the expected range of the readout will be somewhere between the low line in blue and the high line in red. The graph on the left is a zoomed version of the one on the right, showing what happens in the 50 milliamp range and the blank out zone of 50 milliamps and below. As you can see, whatever the green accurate value is in this area, you only get 0, which then jumps to the actual readout. For voltage, it's a lot simpler because there's only one accuracy, namely 1% for the whole range. For example, for a real voltage that's exactly 5 volts, we can expect to see a readout between 4.95 and 5.5 on a UT658 display that meets its specification. My intention was to run a couple of simple tests to check the accuracy of the USB tester. A bench power supply to provide adjustable voltage to a USB socket, and to check the input current. A USB plug with open leads going to a voltmeter and through an amp meter through an adjustable load. This isn't very hard, and in principle this is what I was doing, but as often reality turned out to be a lot more messy than a nice diagram. One of the major issues is the voltage drop across leads and cables. For example, if you are measuring millivolts, that affect even reasonably thick cables at surprisingly low currents. For example, it turned out that I needed to measure the input voltage directly at the USB socket. Otherwise, the comparison between the UT658 readings is skewed by the voltage drop between the socket and the power supply, despite using good-sized cables for test leads and within the power supply itself. Because the setup is so messy and compact, because I needed to get all those devices and displays into the same shot, I thought I quickly introduce some of the more unusual items separately. The USB socket comes from an old PC front panel. I had to solder extra power connections to the PCB to avoid significant losses through the rather thin cables. I did not want to cut off the original cables, as I may still want to use them later, and therefore this socket is functional but a bit messy on the workbench. In my first try I used an old USB lead with a micro USB connector on the end cut off to expose the bare wires. That worked, but it had shockingly high losses because of the thin wires. Because of that, the cable also got quite warm at high power settings. In the end, I sacrificed another USB connector, stripped it and soldered thick wires as close as possible to the contacts. This is my electronic load. It has other functions as well, but in this video it's used just to draw an adjustable constant current from 200 milliamps upwards in 100 milliamp steps. The unit has its own voltage readout and the current setting is very accurate. It needs its own power supply and it has a cooling fan that can get noisy at higher currents. The electronic load is only good for currents above 200 milliamps. For lower currents I use these 3 220 ohm resistors. Depending on the current needed, I either use 2 in parallel or 3 in parallel. The configuration is easy to adjust with the wire links in the terminal blocks. The bench power supply I'm going to use for this video is a unit I made myself some time ago from components and modules bought on Banggood, which turned out to be quite good. It has a fan, which causes problems when recording video, but for this test series I need its capability to adjust the voltage in small selectable steps, which is something my other less noisy power supplies don't have. For the first run, I wanted to test the behavior of the UT658 at low current. Because of the fan noise and the long and boring test series, I will be using stills like this one to explain the setup and then show all the test videos significantly sped up and without sound. The red multimeter shows the voltage directly at the USB socket to which the USB tester is connected. At higher currents, there will be some voltage drop in the leads from the power supply to the socket, which reduces the voltage that the USB tester sees as input voltage. The multimeter experiences the same drop and therefore allows accurate comparison with the USB tester readings. For this test, the current is so low that there's practically no effect, but the multimeter offers a higher resolution, so I kept it in place. The output is connected to the blue multimeter as a current monitor to a set of 3 220 ohm resistors. In this run, 2 are in parallel, making a 110 ohm load, while the most right one is not used. I'm going to increase the input voltage in 200 millivolt steps, which will also increase the current through the resistor at the output. At each step, I record the values of all displays for later analysis. We have almost reached the voltage limit of the UT658. To get a few more readings, I am now adding the third resistor in parallel, which reduces the combined resistance from 110 down to 73 ohms. The lower resistor causes more current to flow at lower voltage. You may wonder why I did not use the 3 parallel resistors from the start, and the reason is that I wanted to begin with a current well below the blank-out current of 50 milliamps, but with 3 parallel resistors the necessary input voltage would have been below 2 volts, which makes the UT658 display too dim to be able to read it. This is the collected data, which may look daunting, but it's reasonably straightforward. Let me walk you through it. First of all, there is this horizontal gap. This is when we switched from 2 resistors to 3 resistors in parallel. The readout from all the displays are in the first 5 columns. Here we have input voltage from the red multimeter, the input amps from the power supply. The UT volts is what the USB tester showed as voltage. I'm using UT as an abbreviation for USB tester. The UT amps is what it showed as its current, and the output amps is what the blue multimeter recorded as current flowing to the load. The next 4 columns are calculated based on these measurements. Input minus output in amps shows the difference between the input and output currents. If you just look at it, you see that we get more current in than flows out, so there's always a difference, and this column shows that difference, which actually is basically what the USB tester consumes for its own internal electronics, like its ADC, its processor, LCD and backlight. Error against input current shows how much in percent the current displayed on the USB tester differs from the input current. So this is input current, USB tester current, and this is the error values based on that. Error out is the same, but the USB tester current reading against the output current. So that's this column. And the error against input voltage shows how much in percent the voltage displayed on the USB tester differs against the input voltage. Let's go through some observations. The consumption seems to be pretty constant, about 5 milliamps through the whole of the test series. Here we have the expected gap where the USB tester shows 0 at very low currents. The data sheet says until 50 milliamps, but we can see it starts to come alive at about 40. Other than that, we can see widely fluctuating errors on the current display. The voltage errors are pretty constant and below 1%, which is what we expect from the data sheet. Here we have a graphical representation of the data. Again, the gap here is where we switched from 2 to 3 parallel load resistors. The distance between the blue and the yellow line is caused by the current used by the USB tester internally. The graph explains the seemingly wild errors that are caused by the relative coarse resolution of the USB tester. It starts to come alive at 40 milliamps, but remains at that reading until 50 milliamps is reached. So any currents between the displayable values, like 43, 47, 49 milliamps, cause an increasing error, which drops back to 0 as soon as the next displayable value is reached. The resolution is 10 milliamps, so as the current increases, this becomes less and less noticeable as a percentage from the overall value. One of the reasons why I did this low current test is that I tried to establish if the USB tester includes its own consumption in the readout or not. If the schematics would look like this, then the current that is used by the processor flowing through the sensor would be included. If the schematic would look like this, then the processor and all that consumption would flow separately, and the current sensor would only measure the current that flows to the load. It starts out as if it's the pure output current because its display switches in sync with the yellow line, but it soon moves towards the blue line representing the input current, including the internal consumption. On the whole, I assume it measures the input current, which includes its own current, and therefore resembles the second schematic at the bottom. One wonders if the strange suppression on any current measurement data below 50 milliamps and the internal consumption of around 5 milliamps isn't connected. It looks to me as like a design decision intended not to confuse people by seemingly showing current flow even if nothing or very little is connected, until the real load is an order of magnitude that is a factor of 10 higher than the internal current. For voltage, the case is much more straightforward. The gap in the middle is more noticeable because the lower load resistor needed less input voltage, and therefore the second run starts with a repeat of some voltages. The input and the USB tester readings are right on top of each other. The arrow bars represent the plus-minus 1% accuracy from the datasheet, and the readings are definitely inside. For this test run, we want higher currents, so I replaced the resistors with the electronic load. The electronic load has its own voltage readout, and the current setting in amps is on this display. I replaced the red multimeter for measuring the input voltage with the blue one because it has a slightly higher accuracy and it doesn't annoyingly beep after 10 minutes to turn itself off. This test run is at a fixed voltage of 5 volts, and I'm going to ramp up the load in 200 milliamp steps. Here are the results. Let's start with the easy part. The voltage is fine and well in the 1% tolerance for all test steps. The reason that it goes down at higher currents is because of the voltage drop on the leads to the power supply. The current accuracy is more tricky. The spec set 3% below 500 and 1% and 2 digits above 500. On the surface, the difference between the displayed and the actual value exceeds the 1% in many places, but that does not take into account the digits part of the spec. To do that, I calculated for each USB tester current value in this column the actual minimum and maximum current values that would cause this display and still be inside the spec, taking full account of both percentage and digits part of the datasheet. These min and max values are these two columns here. So for example, an input current of 0.803 amps caused a display of 0.82 on the USB tester. On the face of this is an error of 2.1%, but based on the full accuracy specification, a readout of 0.82 can be caused by actual currents of 0.79 to 1 up to 0.8485. And as you can see, the 0.803 is within this range. So the USB tester still meets its specification. The min-max values are also shown as error bars on this graph, and as you can see, it gets tricky for the USB tester the higher the current goes. In fact, the last two measurements have fallen outside, and that means the USB tester no longer meets its specification for the 2.8 and 3 amp test steps. For example, 3.007 amps, but the allowed maximum range to be within spec would be 3.0198, so it's definitely below and therefore out of spec. To finish off, let's check the capacity metering of the UT658. I have set a load current of 1 amp, that is 1000 milliamps, which should therefore produce exactly a milliamp hour reading of 1000 after 1 hour. After half an hour, we should see the counter reaching 500. It's about 2 seconds late in reaching 1000 after 1 hour of testing. It is interesting to note that most of the time the USB tester was displaying a current of 1.02, that is 1020 milliamps. Based on that value, it should have reached the 1000 count about 70 seconds earlier from what we saw. This made me wonder if the tester's capacity calculation is based on an internal current value with slightly better resolution than the one displayed. To test that theory, I did another test with a current of 46.25 milliamps, showing as 0.04, and timed the first 4 increments of the counter. Here you see the times when the capacity counter incremented. I used the video in slow motion to get as exact timing as possible. For some reason the first interval is a bit shorter than the others, but even then the calculated current is much closer to the displayed 40 milliamps than to the actual 46 milliamps. Accumulated over 4 counts, this becomes almost exactly 40 milliamps. So on the basis of that, at least at very low currents, it doesn't appear that the capacity calculation uses a more accurate current value than what's displayed. For the record, I tried the same test with 36 milliamps, which as we know shows a 0 on the display, and the capacity counter did not increment at all. So if you, for example, leave a battery connected to the USB tester to a charger overnight, it may receive 36 milliamps trickle charge for 10 hours, adding 360 milliampere hours to the battery without the USB tester showing anything of that happening in either the current or its capacity displays. So what do we make of the UNI-T UT658? The displayed voltages are quite accurate. The only slight annoyance for me was that the display update is rather slow, about once per second, and after a change it can take 2 seconds before the display settles on the final value. I suppose this is only an issue when you're doing test runs with frequent changes as I did. In normal operation, it's quite unlikely to be noticed. The current readings are not so straightforward, and we need to differentiate between low and high current. At low currents we have a blank out of below 40 milliamps. This behavior of a tester is quite cheeky because the zero display could lead you to thinking that no current is flowing when in fact it could be almost 40 milliamps. In my book, a device used for testing and troubleshooting should always show what's going on. Another thing on the low currents is the relative coarse resolution. Anything measured could be on principle 10 milliamps off, and then there's the 5 milliamp drain added by the USB tester itself. So if you troubleshoot or investigate consumption of low current devices or trickle charging, the readout of this tester serves as best as a rough indication, and you will need to rig proper meters for accurate measurements. For higher current, say 150 or 200 milliamps and higher, these effects are less noticeable and the current readings of the tester are useful. At the high currents near the end of the range, the accuracy could be better, but the need for very accurate readings at 3 amps from a USB port is probably not that common. The capacity counter seems reasonably accurate as long as you are aware that low currents can still flow without being displayed or included in the capacity count. Thanks for watching.